It is generally not recommended to round off fault current values for economic reasons. Fault current rating of the bus is determined by the maximum fault current that can flow through the bus under fault conditions. Rounding off the fault current value can lead to an underestimation of the maximum fault current, which can have serious consequences. For example, if the fault current rating of the bus is underestimated, the bus may not be able to withstand the actual fault current, which can lead to the bus failing and causing a power outage. Additionally, rounding off the fault current value can make it more difficult to coordinate the protective devices in the system, which can lead to increased downtime and equipment damage. It is generally better to specify the next standard rating for bus protection, even if it is more expensive. This will ensure that the bus is able to withstand the maximum fault current that can flow through the bus, and it will make it easier to coordinate the protective devices in the system. When dealing with fault current calculations in bus protection, several critical factors must be considered to ensure the safety and reliability of electrical systems. Firstly, understanding the fundamental principles of fault current is essential. A fault current is an abnormally high electric current resulting from a short circuit. This short circuit can occur due to various reasons, such as insulation failure, equipment malfunction, or accidental contact. The magnitude of the fault current is determined by the system voltage, the impedance of the circuit up to the fault location, and the type of fault. Secondly, accurate fault current calculations are crucial for selecting appropriate protective devices, such as circuit breakers and fuses. These devices are designed to interrupt the flow of fault current within a specified time, preventing damage to equipment and minimizing the risk of electrical hazards. Fault current calculations involve determining the maximum and minimum fault current levels at different points in the electrical system. The maximum fault current is used to select the interrupting rating of the protective devices, while the minimum fault current is used to ensure that the protective devices will operate reliably under all fault conditions. Thirdly, busbars play a significant role in electrical power distribution systems. Busbars are conductive bars used to collect and distribute electrical power from incoming feeders to outgoing circuits. They are typically made of copper or aluminum and are designed to carry large amounts of current. The fault current rating of a busbar is the maximum fault current that the busbar can withstand without being damaged. This rating is determined by the busbar's material, size, and construction. Fourthly, protective device coordination is essential for ensuring that the protective devices in an electrical system operate in a coordinated manner. This means that the protective device closest to the fault should operate first, isolating the faulted section of the system while minimizing the impact on the rest of the system. Protective device coordination involves selecting the appropriate time current characteristics for the protective devices, taking into account the fault current levels at different points in the system. Fifthly, standards and regulations provide guidance on fault current calculations, bus protection, and protective device coordination. These standards and regulations are developed by organizations such as the Institute of Electrical and Electronics Engineers, the National Electrical Manufacturers Association, and the National Fire Protection Association. Adhering to these standards and regulations helps ensure the safety and reliability of electrical systems. For example, the National Electrical Code, or NEC, provides guidelines for overcurrent protection in Section 240. Specifically, Article 240.4 addresses the protection of conductors against overcurrent, requiring that conductors be protected in accordance with their ampacities. Furthermore, the NEC mandates that equipment be suitable for the available fault current, that is, terminals. This requirement underscores the importance of accurate fault current calculations in the selection of equipment with adequate interrupting ratings. Ignoring these requirements can lead to catastrophic failures and pose significant safety hazards. Similarly, IEE standards offer detailed methodologies for calculating fault currents and coordinating protective devices. IEE Standard 141, also known as the Red Book, provides guidance on power distribution system design, including fault current calculations and protective device coordination. IEE Standard C37.13 provides specifications for high-voltage circuit breakers, including their interrupting ratings and operating characteristics. These standards are essential resources for electrical engineers and technicians involved in the design, installation, and maintenance of electrical systems. In addition to standards and regulations, several other factors should be considered when dealing with fault current calculations and bus protection. Firstly, the system grounding method can significantly impact the magnitude of fault currents. Grounded systems, such as solidly grounded and low resistance grounded systems, typically have higher fault current levels than ungrounded systems. Therefore, the system grounding method should be carefully considered when performing fault current calculations and selecting protective devices. Secondly, the presence of distributed generation, such as solar photovoltaic systems and wind turbines, can increase fault current levels in the electrical system. Distributed generation sources can contribute fault current to the system, which must be taken into account when performing fault current calculations and selecting protective devices. Thirdly, the aging of electrical equipment can affect its ability to withstand fault currents. As equipment ages, its insulation can degrade, and its mechanical components can weaken, making it more susceptible to damage from fault currents. Therefore, regular maintenance and testing of electrical equipment are essential for ensuring its continued ability to withstand fault currents. Ignoring these factors can lead to inaccurate fault current calculations and inadequate bus protection. To illustrate the importance of accurate fault current calculations and proper bus protection, consider a scenario where a fault occurs on a busbar in an electrical substation. If the fault current rating of the busbar is underestimated, the busbar may not be able to withstand the actual fault current. This can lead to the busbar melting or exploding, causing a power outage and potentially injuring personnel. Furthermore, if the protective devices are not properly coordinated, the fault may not be cleared quickly, leading to further damage to equipment and prolonged downtime. In contrast, if the fault current rating of the busbar is properly selected and the protective devices are properly coordinated, the fault will be quickly isolated, minimizing the impact on the rest of the system. This will prevent damage to equipment, reduce downtime, and protect personnel from electrical hazards. Therefore, it is essential to prioritize safety and reliability over cost when dealing with fault current calculations and bus protection. While it may be tempting to round off fault current values for economic reasons, the potential consequences of doing so can be severe. Specifying the next standard rating for bus protection ensures that the busbar is able to withstand the maximum fault current that can flow through it, and it makes it easier to coordinate the protective devices on the system. This will help prevent power outages, reduce downtime, and protect personnel from electrical hazards. In summary, accurate fault current calculations and proper bus protection are essential for ensuring the safety and reliability of electrical systems. Rounding off fault current values for economic reasons is not recommended, as it can lead to underestimation of the maximum fault current and potential equipment failure. Specifying the next standard rating for bus protection ensures that the busbar is able to withstand the maximum fault current that can flow through it, and it makes it easier to coordinate the protective devices in the system. This will help prevent power outages, reduce downtime, and protect personnel from electrical hazards. Always prioritize safety and reliability over cost when dealing with fault current calculations than bus protection. Understanding the components involved is also helpful. Firstly, circuit breakers are mechanical switching devices capable of carrying and interrupting normal and fault currents. They are essential for protecting electrical equipment and personnel from overcurrents and short circuits. Circuit breakers are designed to trip automatically when a fault current exceeds a predetermined level, interrupting the flow of current and preventing damage. Secondly, fuses are overcurrent protective devices that contain a fusible link. When a fault current flows through the fusible link melts, interrupting the circuit and protecting the equipment downstream. Fuses are simple, reliable, and cost-effective overcurrent protection devices. Thirdly, relays are protective devices that sense abnormal conditions in an electrical system and initiate a tripping signal to a circuit breaker. Relays can detect overcurrents, undervoltages, overvoltages, and other abnormal conditions. They are used in conjunction with circuit breakers to provide comprehensive protection for electrical systems. Fourthly, current transformers, or CTs, are used to measure the current flowing in a circuit. They provide a scaled-down replica of the primary current, which can be used by protective relays and metering devices. Current transformers are essential for accurate measurement and protection of electrical systems. Fifthly, voltage transformers, or volts-TS, are used to measure the voltage in a circuit. They provide a scaled-down replica of the primary voltage, which can be used by protective relays and metering devices. Voltage transformers are essential for accurate measurement and protection of electrical systems. Also consider the types of faults. Symmetrical faults, such as three-phase faults, involve all three phases of the electrical system. These faults result in high fault current levels and require high interrupting capacity protective devices. Unsymmetrical faults, such as single line-to-ground faults, line-to-line faults, and double line-to-ground faults, involve only one or two phases of the electrical system. These faults typically result in lower fault current levels than symmetrical faults, but they can still cause significant damage if not properly protected. The location of the fault also matters. Faults can occur at various locations in an electrical system, such as on busbars, in transformers, in cables, or in motors. The location of the fault affects the magnitude of the fault current and the type of protective devices required. Faults close to the source of power, such as at the substation busbar, typically result in higher fault current levels than faults further downstream. Finally, aging infrastructure is often a cause. Many electrical systems are aging, and their components are nearing the end of their useful lives. Aging equipment is more susceptible to failure and can increase the risk of faults. Regular maintenance and testing are essential for identifying and addressing potential problems before they lead to faults. Upgrading aging equipment with newer, more reliable components can also improve the safety and reliability of electrical systems. In addition to the above points, it's crucial to understand the impact of different grounding methods on fault current. The grounding system significantly influences the magnitude and path of fault currents, thereby affecting the selection and coordination of protective devices. Firstly, solidly grounded systems provide a low impedance path for fault currents to return to the source. This results in high fault current levels, which necessitate the use of protective devices with high interrupting ratings. Solidly grounded systems are commonly used in low voltage applications where it is desirable to quickly clear ground faults. Secondly, impedance grounded systems, such as low resistance grounded and high resistance grounded systems, introduce impedance in the ground path to limit the magnitude of fault currents. This reduces the stress on equipment and allows for the use of protective devices with lower interrupting ratings. Impedance grounded systems are often used in medium voltage and high voltage applications where it is desirable to reduce the risk of equipment damage and transient overvoltages. Thirdly, unbranded systems do not provide a direct path for fault currents to return to the source. This results in very low fault current levels during a ground fault. However, ungrounded systems can experience transient overvoltages, which can stress equipment and insulation. Ungrounded systems are sometimes used in critical applications where it is desirable to maintain service during a ground fault, but they require careful monitoring and maintenance to prevent overvoltages. The choice of grounding system depends on various factors, including the system voltage, the type of load, the desired level of protection, and the applicable standards and regulations. A thorough analysis of the system grounding is essential for accurate fault current calculations and proper selection of protective devices. The coordination of protective devices in electrical systems is a critical aspect of ensuring reliable and safe operation. Protective device coordination involves selecting and setting protective devices such as circuit breakers, fuses, and relays so that they operate in a coordinated manner to isolate faulted sections of the system while minimizing disruption to the rest of the system. Firstly, time current curves, or TCCs, are graphical representations of the operating characteristics of protective devices. TCC plot the operating time of a protective device as a function of the fault current. They are used to coordinate the operating times of different protective devices in the system, ensuring that the device closest to the fault operates first. Secondly, coordination studies are engineering analyses performed to determine the appropriate settings for protective devices. Coordination studies involve calculating fault currents at various points in the system, plotting TCC for the protective devices, and adjusting the settings of the protective devices to achieve the desired coordination. Thirdly, selectivity refers to the ability of protective devices to isolate faulted sections of the system without causing unnecessary tripping of other protective devices. Selectivity is achieved by coordinating the operating times of the protective devices so that the device closest to the fault operates first. Fourthly, sensitivity refers to the ability of a protective device to detect and respond to low-level fault currents. Sensitivity is important for protecting against high impedance faults, which may not result in high fault current levels. Fifthly, speed refers to the operating time of a protective device. Faster operating times can reduce the duration of fault currents and minimize the risk of equipment damage. Proper protective device coordination is essential for minimizing downtime, protecting equipment, and ensuring the safety of personnel. In addition to the above, it is also important to consider the impact of harmonic currents on fault current calculations and bus protection. Harmonic currents are currents with frequencies that are integer multiples of the fundamental frequency of the electrical system. They are typically generated by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Firstly, harmonic currents can increase the root mean square, or RMS, value of the current flowing in the electrical system. This can lead to overheating of equipment, such as transformers and conductors, and can reduce their lifespan. Secondly, harmonic currents can distort the voltage waveform, which can cause malfunction of sensitive electronic equipment. Thirdly, harmonic currents can interfere with the operation of protective devices, such as circuit breakers and relays. Harmonic currents can cause protective devices to operate incorrectly or to fail to operate when they are needed. To mitigate the effects of harmonic currents, harmonic filters can be installed. Harmonic filters are designed to reduce the amplitude of harmonic currents in the electrical system. They typically consist of capacitors and inductors that are tuned to specific harmonic frequencies. Also, regular power quality monitoring can help to identify and address harmonic current problems. Power quality monitoring involves measuring the voltage and current waveforms in the electrical system to detect the presence of harmonic currents. The data collected from power quality monitoring can be used to determine the appropriate corrective measures. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. Electrical systems are complex and require careful design, installation, and maintenance to ensure their safe and reliable operation. Always consult with a qualified electrical engineer or technician for specific recommendations regarding fault current calculations, bus protection, and protective device coordination. Furthermore, continuous education and training are essential for staying up to date on the latest standards, regulations, and best practices in electrical safety. Participating in industry conferences, attending workshops, and reading technical publications can help electrical engineers and technicians to enhance their knowledge and skills. Remember, safety should always be the top priority when working with electrical systems. Following established safety procedures, wearing appropriate personal protective equipment, and using properly maintained tools can help to prevent accidents and injuries. By understanding the principles of fault current calculations, bus protection, and protective device coordination, and by adhering to established safety practices, we can help to ensure the safety and reliability of electrical systems for ourselves, our colleagues, and the public. Finally, remember that the consequences of neglecting safety can be severe, ranging from equipment damage and power outages to serious injuries and fatalities. A proactive approach to safety, with a focus on prevention and continuous improvement, is essential for creating a safe and productive work environment.